Clap your hands at one end of a long tube of air. The news races away at 340.2 meters a second. Now take the very same tube up to 10 kilometers, cruising altitude, and the very same clap only manages 299.5. Same tube. Same gas. What on earth changed? Up there the air is much thinner, you just watched most of the molecules leave. And the pressure is far lower. Either one of those looks like a perfectly good culprit. Hold on to both of them, because by the end of this video I am going to strike them both out, and the real answer is not on that list. Here is the whole plan. To work out how fast that news travels, we need three ingredients: mass does not vanish, force equals mass times acceleration, and one single result you already earned in a last video, plus the perfect gas law, and one number I am going to borrow rather than derive. That is the lot, and I promise you the answer is going to be stranger than you expect. Those four empty slots along the top are the four results we are going to fill in. First, what is it that actually moves? Sound is not a wind, and here are 2 meters that are going to prove it, both drawn to the very same scale, how far the front gets, and how far one molecule gets. So keep your eye on this one molecule, ringed in white, and on the grey line marking exactly where it is standing right now. The green front is on its way. There it goes. The front sweeps past, and look what our molecule actually does. It gets shoved, it shoves its neighbor, and then it just stands there. Look at the 2 meters. The green one is running away across the screen. The gold one has not left the mark. It did not set off down the tube with the sound. It passed the message on and stayed put. It is a stadium wave. Here is the ground, and here are the people in it. Watch one of them, the ringed one, with a dashed line at her seat. The wave travels all the way round the ground at a tremendous rate, and not one single person changes seats. Everybody stands up, sits down, and stays exactly where they were. What travels is the pattern, not the crowd. And the shove is feeble. That is the second thing to hold on to. The front itself charges along at the speed we are after, call it A, the long green bar. The gas behind it creeps forward at a speed hundreds of times smaller, that blue sliver, which I have drawn far bigger than it really is, because at true scale it would be thinner than 1 pixel. We will write that tiny speed dA, and it is the same dA you will see again in a minute. Everything about a sound wave is tiny, a hair denser, a hair warmer, a hair of a shove. Which means that from here on, a little d in front of a symbol means exactly one thing, a tiny nudge of. So dρ is a tiny nudge of density. dP is a tiny nudge of pressure. And dA is a tiny nudge of speed. Nothing more frightening than that. Right. Let us go and stand on the front. Hop on board, and from up here the front is not moving at all, instead the gas comes rushing at you from the right, gets squeezed as it goes through, and streams away behind you on the left. On the right is gas that has not heard a thing yet. Relative to us, it arrives at speed A, that is the speed of sound, the number we are hunting, with density ρ and pressure P. On the left is gas that has just been hit. It leaves a touch slower, a minus dA. A touch denser, ρ plus dρ. And at a touch more pressure, P plus dP. 3 tiny nudges, and every one of them is the wave doing its work. Ingredient 1. Nothing is created or destroyed inside that box, so the mass arriving every second has to equal the mass leaving every second. And where does that come from? A is the tube's cross-section, the face you see looking straight down it. In 1 second the gas sweeps through a slug of tube exactly along that shaded block. Its volume is A times A, so its mass is the density times A times A. That is the mass past any station, every second. So write it down. In from the right, ρ, A, out to the left, the new density, ρ plus dρ, times the new speed, A minus dA, times the same area A. The tube does not change width, so that A is the same A on both sides, 1 factor of A on the left, 1 on the right. Strike them both, and the area is gone for good. Now multiply the right-hand side out, bracket by bracket. Rho times A, plus A times D rho. Minus rho times dA. And minus D rho times dA. 2 deletions, and both are honest. First, there is a rho A sitting on the left and an identical rho A sitting on the right. Take the same thing off both sides of an equal sign and the equal sign still holds, so they go. Second, look at that last term. It is a tiny nudge multiplied by another tiny nudge. Here is what that means with real numbers. If each nudge is 1,000th, then their product is 1,000,000th, 1,000 times smaller than the terms we are keeping. It is not 0, but next to the others it may as well be, so we drop it. What survives is beautifully simple. 0 equals A times D rho, minus rho times dA, move 1 across, and there it is, rho times dA equals A times D rho. The slowdown of the gas and the density bump are locked together. That is ingredient 1, banked. Up it goes into the first of those 4 slots, and everything we earn from here on fills the next one, so you can always see exactly what we have got. Park that result down in the corner as well. Now ingredient 2, force equals mass times acceleration, written for a stream of gas. What is pushing on the stuff inside our box? Only pressure. And before we add anything up, let us fix a convention. The gas is flowing right to left, and we are going to count that direction, leftwards, as positive. Now, the gas on the right is the upstream gas, and it pushes leftwards with P. The gas on the left is the downstream gas, and it pushes back rightwards with P plus dP. Add those up, counting leftwards as positive. The upstream face pushes us along with P times A. The downstream face pushes back against us with the slightly bigger P plus dP, times the same A, multiply that bracket out and you get PA minus dPA. The two PA terms are identical, so they cancel, and everything is gone except the little difference. The net force is minus dP times A. The minus sign just says what your eyes already told you, the bigger push is the one coming back at us. Now the other side of Newton's law, and there is one regroup to do first. Acceleration is just change in speed per second. So mass, times change in speed per second, is exactly the same product as mass per second, times change in speed. We simply move the per second onto the other factor. And kilograms per second is the same rho AA we drew that slug for a moment ago. Multiply it by how much the speed changes on the way through, in at A, out at a minus dA, so the change is minus dA. Set the two sides equal and this is Newton's second law for our little box of gas. 2 more strikes, and you have seen both before. Same tube, same A, out they go. Minus on the left, minus on the right, multiply through by -1 and they both flip away. What is left is momentum's answer, the pressure nudge equals rho A times the speed nudge. Ingredient 2, banked. Up it goes, into slot 2. 2 boxes, 2 laws, 2 lines, and look at what they share. Continuity ties rho dA to a d rho. Momentum has a rho dA sitting right there inside it. So one goes straight into the other. Momentum says dP is rho times A times dA. Group it differently, that is allowed. Multiplication does not care about the order, and it reads A times the clump rho dA. And continuity told us exactly what that clump is. It is a d rho. Swap it in. And now A times A. 2 A's multiplied together is A squared. Divide both sides by d rho, and there is the first real answer of this video. So hop back off the front. And stop and read that, because it is worth more than it looks. The speed of sound, squared, is a slope, how hard the gas pushes back when you squeeze it. Up it goes on the ribbon. Now squeeze these 2 boxes the same amount. The stiff one answers with a leap of pressure, sound in it is fast. The floppy one barely notices, sound in it is slow. But there is a catch buried in that innocent little slope, and it is the entire reason this video exists. How much does the pressure rise when you squeeze the density? Squeeze it how? Because there is more than one way to squeeze a gas, and they do not give the same answer. Here are two identical boxes of the same gas, each with a thermometer in it. Squeeze the left one slowly. Take all day about it, and let every scrap of heat leak out to the room. Those are the heat arrows leaving through the lid. Watch its thermometer, it does not move. The gas never actually warms up, its temperature stays put the whole way, and the pressure climbs along this gentle orange curve. Now the right one. Slam it so quickly that the heat has nowhere to go, the arrows are crossed out, nothing gets across. And look at that thermometer, the gas warms up as you compress it. A warm gas pushes back harder, so its pressure climbs this much steeper purple curve instead. Same gas. Same starting point. Same amount of squeeze. Two completely different answers. And here is a number worth remembering, because you are going to meet it again in about 2 minutes. Give both curves exactly the same run along the bottom, the same squeeze in density. Then measure the steepness of each one, how far the straight edge resting on each curve rises over that same run. The steep one is not vaguely bigger. It is bigger by exactly the factor gamma, the ratio of specific heats you met in the last video. For air, gamma is 1.4. I will prove that number to you in a couple of minutes, once we have the algebra for both curves. So which squeeze is a sound wave? Two answers, and they are the two halves of the word. Answer 1, the squeeze is feeble. Almost nothing happens. There is no slamming, no friction worth the name, nothing wasteful, run the film backwards and nothing you saw would look impossible. That is what reversible means, and this is exactly why the wave being weak matters. Answer 2, the front is thin, and it goes past in 1/1000th of a second or less. Heat is slow. It simply has no time to cross from the warm side to the cold side before the whole thing is over. No heat in, no heat out. That is adiabatic, and this is why the wave being fast matters. Reversible and adiabatic together is one word, and it is the word you spent the whole last video on, isentropic. Entropy, how scrambled up the gas is, does not move. So it is the steep purple curve we want, and I am going to hang that fact in the corner where you can see it for the rest of the video. Which means our answer needs one extra mark on it. A little s hanging off the bracket, and all that s says is, take this slope along the steep curve, the one where entropy does not change. That tiny letter is about to be worth about 50 meters a second, so watch it go up and land on the answer already hanging on the ribbon. Now for ingredient 3, and it is the one you already earned. Last video you got exactly one line about isentropic gases, and this is it, P times V to the gamma is a constant. Little v is the room 1 kilogram of gas takes up, which is just 1 over the density. So substitute P times 1 over rho, all to the power gamma, equals the constant. Turn the fraction the right way up, 1 over rho to the gamma flips to rho to the gamma on top, and the rung becomes, pressure equals a constant, times density to the power gamma. To get the slope of that curve we need one tool, and only one, the power rule. When you find the slope of x to the n, the exponent walks out to the front and what is left drops by 1. Watch it happen. X cubed, the 3 steps down off the shoulder, lands out in front, and the cube becomes a square. Apply it. C is just a fixed number so it comes along for the ride. The gamma walks out to the front, and rho to the gamma becomes rho to the gamma minus 1. And notice the little s is still there, we are on the steep curve and we are staying on it. Now a move that looks like cheating and is not. Rho to the gamma minus 1 is simply rho to the gamma, divided by 1 more rho, subtracting 1 from an exponent is the same as dividing by one of them. Which means this clump on top, c rho to the gamma, is something we have already met. Look down at the rail card in the corner, the one I pinned there on purpose. C rho to the gamma is exactly what we called P. So the whole clump collapses, the slope is gamma, times P over rho. The perfect gas law. You met it as PV equals RT, and V is 1 over rho, the same swap you already watched. So put 1 over rho in for V, and PV becomes P over rho, nothing but R times T. R is S gas constant, one fixed number, 287 joules per kilogram per Kelvin. And now we can pay off the promise I made at the graph. What is the slope of the gentle curve? On that one the temperature never changes, so RT is just a fixed number, and P equals that fixed number times rho, a straight line. The slope of a straight line through the origin is the number in front, RT, which is P over rho. So divide the steep slope by the gentle one, gamma P over rho, divided by P over rho. Everything cancels except gamma. Exactly gamma. Now it is earned. Right, back to the steep slope, and put P over rho equals RT straight into it. The slope is gamma RT. And the slope was a squared. So a squared is gamma RT, and take the square root of both sides. There it is. The speed of sound in any perfect gas, the square root of gamma RT up it goes into the last slot, and it stays there. And look up at the air, the moment T walks into the answer, the gas is the subject again. Now read what is on that line, and much more importantly, read what is not. Gamma, a property of the gas, 1 point for air. R, also a property of the gas, 287 joules per kilogram per Kelvin. And T. That is the entire list. There is no density in that formula. Density walked into the derivation, you watched it go in, and it walked straight back out. Suspect 1, innocent. And there is no pressure in that formula either. Same story. Suspect 2, innocent. I told you at the start I would strike them both out. The speed of sound in a gas depends on exactly one thing you can change, its temperature. Not its pressure. Not its density. Not the altitude, except through the temperature. That is the whole punchline of this video, and if you remember nothing else, remember that. If that feels wrong, good, it felt wrong to me too. Sound is a pressure wave. Surely more pressure means faster sound? So watch what actually happens when you squeeze a box of gas and keep its temperature fixed. Here is the box, with a fixed number of molecules in it, and here are 3 bars, the pressure, the density, and the ratio of the two that our formula actually cares about. Push the lid down. Squash the gas into half the room. The pressure doubles, up goes the red bar. But the density doubles too, because you have the same molecules in half the space, up goes the gold bar with it. And the ratio? The ratio does not move a millimeter. Twice as much, over twice as much, is exactly the same as before. And there is a better reason underneath all of it. Temperature is how fast the molecules are flying, here they are, already tearing about. Their root mean square speed, which just means their typical speed, is the square root of 3 RT, at 288 Kelvin, about 500 meters a second. I am borrowing that one from kinetic theory rather than deriving it, the only number here I am asking you to take on trust. A sound wave is handed from molecule to molecule, so it can never get much faster than the molecules doing the handing. Here is their speed, and here is ours, drawn to the same scale. Divide one by the other and it collapses to the square root of gamma over 3, for air, about 68%. And that fraction holds at any temperature because both speeds carry the same square root of T. Which finally explains the density. Pack the molecules closer together, on the top rail, and the message does get handed on more often, but each handoff covers less ground. Spread them out on the bottom rail and it is the other way round. Watch the 2 green messengers, they arrive together. Those 2 effects pull opposite ways and cancel, and we did not just claim that, we watched it happen with the piston a minute ago, when P and rho doubled together and their ratio never moved. The only way to make the message move faster is to make the messengers themselves faster. And the only way to do that is to heat them up. Watch, and watch the card underneath. Right. Numbers. Sea level, 288 Kelvin. Gamma R is 1.4 times 287, 401.8, fixed forever for air. Times the temperature, about 115,718. Now the units. R is joules per kilogram per Kelvin, so R times T is meters squared per second squared, which means its square root is a speed. 340.2 meters a second, the number I put on screen in the first 10 seconds of this video. And gamma never changes for air, so root 401.8 is almost exactly 20. The speed of sound in air is about 20 root t. At sea level that gives 339.4, against the full formula's 340.2. One piece of history, because it makes this point better than I can. Isaac Newton did this calculation in 1687. He was the first human being ever to work out the speed of sound from first principles, and he got it wrong. His mistake was the one we spent 3 minutes avoiding. He assumed the slow squeeze, the isothermal one, with no gamma in it. So his answer was the square root of RT, and it comes out at 287.5 meters a second. That is the dashed grey line, and it sits stubbornly below the truth everywhere. 52.7 meters a second too slow, at sea level. 15.5% low. And people knew, gunners timing cannon fire across a valley kept measuring a bigger number than the greatest physicist alive had predicted, and they kept measuring it for 130 years. And the missing piece is exactly the thing we were careful about. Newton's square root of RT, over our square root of gamma RT, the R cancels, the T cancels, and all that is left is 1 over the square root of gamma. 0.8 for 5. So Newton's answer is 84.5% of the truth, precisely the gap the gunners were measuring. His whole error was one little letter S. It took 130 years, and Laplace, to put it back. So let us finally answer the question I opened with. Why is the news slower up at 10 kilometers? Not because the air is thin. Because the air is cold. About 15 degrees Celsius down here, about -50 up there. Slide down the temperature axis and the speed of sound slides with it, 340, 320, 299.5. And here is what that costs an aeroplane. Mach number is not a speed. It is a ratio, u, your own speed through the air, divided by a, the speed of sound in the air you happen to be flying through. Same aeroplane, same u, different air, different Mach number. 250 meters a second, the same airspeed all 3 times. That is the blue arrow, and it never changes length. The green bar behind it is the local speed of sound, the yardstick you are being measured against. At sea level, 250 over 340.2, Mach 0.735. At 5 kilometers the yardstick has shrunk, and the same aeroplane is at Mach 0.78. At 10 kilometers it has shrunk again, Mach 0.835. Nothing about the aeroplane changed. Not its engines, not its wings, not its speed through the air. Watch, here is the sea level yardstick laid over the other two, and here is what it actually does. It shrinks. That is why Mach number is a ratio and not a speed, and it is why an aircraft that is perfectly comfortable low down can be shaking itself apart at exactly the same airspeed up high. One last thought to leave you with, and it is the reason this number matters at all. Sound is how a gas warns itself. Every message the air ahead of an aeroplane ever gets, move aside, something is coming, travels at exactly this speed and no faster. So what happens when the aeroplane goes faster than its own warning? The air in front gets no warning at all. It cannot ease aside gently, because nothing told it to. It has to get out of the way all at once, in one violent jump, and that jump is a shock wave. The cone you are looking at is where those warnings pile up. Which is where we go next. First, what happens when you bring a fast flow smoothly to rest, the stagnation properties, and then what happens when you cannot. If you want to feel it rather than read it, drag a source past Mach 1 in the Mach cone game and watch the cone being born. And remember the one line, the speed of sound is a thermometer, dressed up as a speed.